Yuvraj? Yeah, are you sharing the screen?
Hello, is it visible?
Yeah, the screen is visible.
Yeah, screen is visible.
Just you can start.
Okay. Actually, the present. Yeah. Thank you. Okay, so today we are going to present experiment 3. So experiment 3 is divided into two parts. That is part 1 and part 2. So part 1 consists of three things. One is the VI characteristics of PN junction diode. Then you are going to study about half wave rectifier and then full wave rectifier. So now we'll go to the next slide, which is the PN junction diode. Um, please change the slide. Yeah. So yeah, tell me.
I think there's a small lag here. So,
Okay, no problem. In after this PN junction diode, after we study this, we'll be able to explain the structure and function of a PN junction diode, as well as the forward and reverse characteristics of a silicon and germanium diode. And after that, we are going to study half wave and full wave rectification, where we are going to understand what is rectification and half wave rectification in both positive and negative half cycles. And in case of full wave rectification, we are going to study what is a center tapped full wave rectification and bridge full wave rectification. For all of these cases, we are also going to do the simulations in VLAB. Next is the PN junction diode. Yeah, so PN junction diode, basically it's a two-terminal device which is formed from a junction of a p-type and n-type semiconductor. So we know that for an n-type semiconductor, there are free electrons which are the majority carriers, and for p-type semiconductor, holes are the majority carriers. So when an n-type semiconductor is joined with a p-type semiconductor, a PN junction is formed. Now the junction basically in the stable situation, it has no charge carriers, and therefore the particular region is called the depletion region, and the thickness of this region varies with the applied voltage. Now the terminal which is connected to the p-type material is called the anode, and the one which is connected to the n-type material is called the cathode, as you can see from the schematic symbol. And on the right side you can see this is how a PN junction diode looks like. There is a silver strip which basically marks the cathode section, so you can easily distinguish between the cathode and the anode. The next is the forward bias of a PN junction diode. So basically what do we mean by biasing? Biasing basically stands when we apply some external voltage to a PN diode. That is what is called biasing. So when there is no voltage which is applied to a diode, then it is basically called an unbiased diode. So in this situation, the N side is going to have a majority number of carriers, which are the electrons, and very few holes, whereas the P side is going to have majority of holes and very few electrons. So in this particular, in the unbiased situation, the free electrons tend to diffuse to the P side and recombine with the holes present there. Some immobile ions in the N side, and creating some negative immobile ions in the P side of the diode. So the immobile ions in the N side near the they are near the junction edge. Similarly, in the P side it is near the junction edge. So this of all the negative ions accumulate at the junction, and this region is therefore called the depletion region. You can see. So at this region, there is a static electric field which is called the barrier potential is created across the PN junction, and this barrier potential basically opposes further migration of the holes and electrons across the PN junction. Now, in forward bias situation, a diode is said to be forward biased when, as you can see in this diagram, when the negative terminal of the battery is connected to the N side and the positive terminal of the battery is connected to the P side, that is the anode. So as a result, the holes in the P region and the electrons from the N region, they are pushed towards the junction, and this basically neutralizes the depletion region width. Now, if the externally applied voltage becomes larger than the potential barrier voltage is different for silicon as well as germanium diode. It is 0.6 to 0.7 volt for silicon and 0.3 volt for germanium diode. So if it becomes higher than this, the barrier potential opposition is overcome and current starts to flow. This is forward bias. So or the E voltage or the cut-in point. So that at that particular point, that value is actually 7 for silicon, 0.3 for germanium. So beyond that, even with small increase in the voltage, the current starts to drastically increase. And with the application of this forward voltage, the depletion region becomes very thin, and as a result, huge amounts of current flows. So in this situation, the diode basically acts as a short circuit in the forward. Now, positive terminal of the battery is connected to the N side, and the negative terminal is connected to the P side. So the positive voltage which is applied to the N-type material basically attracts the electrons towards the positive electrode and away from the junction. And the negative voltage which is applied to the P side, it basically attracts the holes and towards it and away from the junction. So as a result, the depletion layer grows wider due to the lack of electrons and holes. And therefore, a very high potential barrier is created across the junction, thereby preventing the flow of current through this particular material. So this condition, therefore, it offers a very high impedance path to the current flow, and practically almost zero current flows to the junction with an increase in the bias voltage. But however, there is some minority carrier flow also, and that leads to a very small current, which is called the leakage current. It's in the order of microamperes basically, so it's very small. Now, next we'll go to the static characteristics. So basically over here, what we can see is that the diode acts as an open circuit. Okay, so the diode is basically acting as a switch that is short in case of a forward bias and open in case of a reverse bias. So next we'll go to the static characteristics of the diode. So over here, this is the VI characteristics of a PN junction diode. So here we can see that we know that in order to conduct, for the diode to conduct, the forward bias voltage should be greater than the barrier potential. So in the forward biasing section, that is in the first quadrant, we can see that the voltage, once it is greater than the barrier potential, for silicon greater than 0.7 and for germanium greater than 0.3, the diode starts conducting, and these particular voltages, they are referred to as the knee voltage or the cut-in voltage. After that, even with a small increase in the applied voltage, the current drastically rises. So, and in the third quadrant, what happens? That is, if the reverse voltage, we have very small amount of current, as you can see, which is the reverse leakage current, and that happens up to the time when reverse breakdown voltage is reached. Now, when that breakdown voltage is reached, then the PN junction depletion zone, it basically breaks down, and the current flows due to Zener or avalanche breakdown. And thus there is a steep downward slope, as you can see in the reverse static characteristics. So this is the Zener breakdown or the avalanche breakdown region. So after this, we have the simulation part of the VI characteristics, which will be explained by Yuvraj. So Yuvraj, please go to the VLAB section.
So first I'll try to see if the field VLAB is working. Okay. So here this is the so we have 6 experiments for the VI characteristics of a diode. First we'll see the forward bias SI diode. So here we have to first select the diode here. I'll select this one. So here you can see the cut-in voltage is already mentioned. It is 0.6 volts for this diode. So then
sorry, Yuvraj, because I think there is a lag. Please be a bit slow, okay?
Okay.
Yeah, your screen is now visible. You please carry on, but be a bit slow because there is a lag.
Okay. Okay. So here, as you can see, we will first select the diode here. Then here is the threshold voltage. Sorry, the cut-in voltage for this diode. Here is you can select the resistance for this experiment. I will be selecting it to 100 resistance here. Then this is the DC voltage which is applied here. This is the diode. This is the voltmeter, and this is the ammeter, where we will measure the forward voltage and the forward current. So first, what we have to do is we select the diode voltage to 0.2. We will be moving the voltage from 0.2 to 5 volts. Let's add it to table one by one. So first we will select this point. Here, as you can see, the forward current and the forward voltage is 0, then we'll increase it a bit. It will be 0 until you have reached the threshold voltage, so increase it more than 0.6. So I'm selecting 0.7 here, and then you just add it to the table. You just keep on doing that for all the points. I'll just show this once. Once after you have taken some values, then you just click on plot to get the graph. Here, as you can see, the cut-in voltage is very close to the 0.6. So this is for the forward bias, right? Okay, so similarly, you can do it for different diodes. Different diodes will have different cut-in voltage, so keep that in mind. So this is for the forward bias silicon diode. Okay. So after that, okay, I'll just show one of the draw circuit diagrams. You can do the rest yourself. Okay. So this is for the draw circuit diagram.
Sir?
Yes. Yes, there is a question.
Hello, sir?
Yeah.
Yes, sir. Sir, this VF is already selected for each diode, no, sir?
You cannot select it. It's for the diode, like the diode's inbuilt property. Like
Yes,
it is a
okay,
cut-in
sir.
voltage. So you cannot
Yes.
select this one. Like for germanium and silicon, it will be different. For
So
silicon,
it's not tunable. It's just showing what is the VF value for that particular diode. So you can only select the diode from that drop down. You cannot change the VF value there. It's just showing. I mean, it's just a display.
Okay, sir.
Okay.
Yes, sir.
So, sir, in that experiment report, I have to paste a screenshot of each individual data, or one with that entire table will be sufficient?
So no. What you have to do is that you have to select different diodes, set different voltages, paste the table and the plot. So you are getting one particular table at the left hand side, right?
So, sir,
So for
one single screenshot will be sufficient, sir.
sorry.
So, like for each such data, do you have to take a screenshot, or one single screenshot?
No.
The
One
data is
screenshot for
sufficient?
entire table is perfectly fine, but try to have the table and the plot at two different screenshots, because otherwise the values and the plot will be very small. You have to minimize the screen a lot. So try to have one screenshot for the table and the circuit, and another screenshot for the plot.
Okay.
Okay.
Sir.
Yeah.
So I'll
Yeah.
show.
Please carry on.
Yeah, I'll show one draw circuit, and you can do the rest. Okay. So you just connect these. This is just simply for forward bias, so you already know it here. So as you can see, it will show right, and then you have to, same. It is the same as the first one. So okay. So this is for the forward bias both. Let's look at the reverse bias case. Now reverse bias, everything is the same except the diode position is opposite. It is in the reverse bias mode, and you can see this value. This is now the breakdown voltage value. So this you have to keep in mind. So I'm setting the resistance for 100. Now as you can see, the current won't change as we increase the DC voltage. Now it will remain the same until you have reached the breakdown. Now once it reaches the breakdown, it will rise significantly. Now you simply add it to the plot, and this is the plot of the reverse bias. So this is exactly same, just the reverse bias. Every diode will have different, so keep that too in mind. Okay. So this is in the reverse bias. The in germanium one, it's exactly the same. Here you don't have to select the diode; it's already there. So you just have to see at which point it will start to conduct. Okay, so you first have to select the 1 kilo ohms resistance. Once you select that, you keep on increasing. As you know, germanium is around 0.3, so it will start very, very quickly. So you have to be careful about that. So as you can see, it is close to 0.3. So this is for the germanium diode. Similarly, it will be done in reverse bias as well. So let's get back to the presentation. Question. Hello. Hello.
Yes, I can hear. Hello.
Hello.
Yeah, so we have studied the junction diode characteristics. So now we'll go to the rectification part. So now here we are going to study two types of rectification, half wave and full wave. Now what is rectification? So rectification basically is a process of converting an alternating current to a direct current. And so therefore rectifier is a device which does this. And PN junction diode works as an excellent rectifier. As you can see, it converts an alternating current to a direct current. And there are two types of rectifiers. One we know is a half wave rectifier and the other is the full wave rectifier. So what is a half wave rectifier? Now the next slide. Yeah, so half wave rectification. What happens over here is during the positive cycle of the input applied voltage, the diode is forward biased. As you can see, this there is only one diode firstly in this half wave rectification. So this particular diode is forward biased, and during the negative half cycle, obviously this will be reverse biased. So as we know that a PN junction diode basically has a zero resistance in the forward bias direction in the forward bias situation and offers infinite resistance in the reverse bias situation. Therefore, what will happen is the diode will only conduct in the positive cycle and in the negative cycle it will not conduct. So therefore, we get the half wave rectified output, and as you can see in this output diagram over here. So here the AC input is converted into a pulsating DC output. Pulsating DC means it is not a pure DC. Obviously, there is some, the output contains a reasonable amount of DC and certain small amplitudes of AC signal also. So that is called a pulsating DC output. So therefore, you get this output waveform over here. Now we go to the full wave rectifier. So these are the positive. Okay, these are the positive and negative half cycles of half wave rectifier. So as I told you, during the positive half cycle, you have the diode which behaves like a closed switch. So you have conduction during that, and in the negative half cycle, the diode behaves like an open circuit. So you do not have any conduction. So you get a pulsating direct current at the output if you combine these two. Now we go to the full wave rectifier. So the next slide, yes. So the full wave rectifier basically converts the whole of the input waveform to a constant polarity output. And there are two types of full wave rectifiers we know. One is a center tap and the other is a bridge rectifier. So the center tap structure basically employs two diodes, and they are connected to the opposite ends of a center tap secondary transformer, as you can see over here. So this particular point, that is point C, which is the center tap point over here, it is basically at a zero voltage point or a ground potential point. Now, whenever an AC input is applied to the primary coils of the transformer, so as we know, it is a part of it is sent to the secondary in terms of the turns ratio. So at that point of time, what happens? The points A and B becomes positive and negative alternately. So for the positive half cycle, we have the point A at positive and the center point is at the 0 volt and point B is negative. So in this situation, D1 diode is forward biased and D2 is reverse biased. So D1 is conducting and therefore there is a current flow through the load resistance RL. And during the negative half cycle, the reverse thing happens, that is D1 is reverse biased and D2 is forward biased. So again, there is a flow of current to the load resistance RL, and there is a unidirectional, as you can see, there is an unidirectional current flow. So the rectified output over here, basically you can see that it contains both the, it basically conducts for both the positive and negative half cycles. So you have the entire pulse in the DC form. Obviously, just like I told you in case of half-wave rectifier, here also you're going to have some AC components of minute amplitude, and that is in the form of ripples. So next slide, we have the bridge rectifier section. Yeah, so here basically I've presented a comparison so that you can understand. So the left hand side, as you can see, the center tap full wave rectifier basically has two types of diodes, D1 and D2. And the bridge rectifier, it's a bridge configuration employing 4 diodes, D1, D2, D3 and D4. So during a positive half cycle, 2 diodes are forward biased and 2 are reversed, and same thing happens for the negative half cycle. So, so in this case, for the positive half cycle, D1 and D2 are forward biased, and therefore a current flows through resistance RL. The current path is also shown clearly in this diagram. And during the negative half cycle, again D3 and D4 are forward biased, D1 and D2 are reverse biased, and again unidirectional current flows through the load resistance RL. So in this case also, you're going to have two, like for both the positive and negative half cycle, you are going to have the output. Output is the same for both the cases, just that this is employing 4 diodes, this is employing 2 diodes. So after this, we'll come to some terminologies related to the rectifier section. Yeah, so, these are some important things. First is the rectification efficiency. So rectification efficiency of a diode is the ratio of the DC output power which we obtain to the AC input power, and it is represented as this eta. It is DC by AC input power. And now we go to the ripple factor. So what is the ripple factor? Ripple factor basically is a measure of the effectiveness of the rectifier, and it is given by the ratio of the RMS value of the AC voltage to the DC voltage of the rectifier. And basically it gives the amount of the harmonics which is present in the output DC waveform. So smaller the value of the ripple factor means there is lesser amount of AC component which is present in the output waveform, and therefore your rectifier is more effective. Next, we go to the peak inverse voltage. So peak inverse voltage, which we know as the PIV, that is, it refers to the maximum voltage a diode can withstand when it is non-conducting. So non-conducting is the non-conducting when it is non-conducting in the reverse biased condition. So in the reverse biased condition, the maximum voltage which appears across the diode is the peak inverse voltage which it can withstand. So next, we'll give a comparison. Yeah, so this is a comparison between half wave, full wave and bridge. As you can see, it basically differs in the number of the diodes, that is 1, 2 and 4 for this. Now over here, see the efficiency, rectification efficiency, point number 7, it is less for half wave, obviously, because it is not conducting the negative half cycle. And for full wave and bridge, it is almost, it is actually double that of the half wave. Now ripple factor is more in case of the half wave. And for the full wave and bridge, it is almost 1/3 of that of half wave. And PIV rating for a half wave rectifier is the peak voltage, that is say Vm, if you have Vm sin omega t applied at the input, so the peak voltage. And for full wave center tap, it is twice Vm, and for bridge, it is Vm again. So this is about this, and now we'll go to the simulation part, which Yuvraj is going to explain.
Okay, so let's get to the simulation part. So first, okay, let's first discuss the full wave rectification. Half wave is exactly the similar. So here is the full wave rectifier. So first you have to do is change the resistance here. Once you set the resistance, after that you just turn on the oscillator. Once the oscillator is on, you turn on the input signal wave, and then you get the output at the oscilloscope. Now, as you know, channel 1 is input waveform and channel 2 is output waveform. From the instruction, it is already mentioned. If you have any problem, just follow the instructions. So the channel 1 is input waveform and channel 2 is output waveform. Ground is basically the DC levels, and in dual you can see both channel 1 and channel 2 output. I think you are already familiar with the oscilloscope, but I'll go through it once again. So here you can change the frequency of the input waveform, and here you can change the amplitude. Now here in the controls, you can change the volt per division in the position Y of channel 1, and here you can change the volt per division in channel 2 of position Y. In this you can change the DC input, same for the oscilloscope in the Y in the channel 2. So after that, here you can change the millisecond per division in the x-axis in position X. Same here. Okay. So this is for full wave. I'll let you draw the circuit on your own time. So for half wave it's exactly the same. So once you select the resistance here, you turn it on. After that, you select the sine wave and then the oscilloscope. Here you can see once I dually, as you can see here, the output for the reverse bias is 0, and for the forward bias it is exactly the same as the input. It's the oscilloscope controls are same for the half wave and full wave. So this is about the simulation part, as you know. So are there any questions?
Sir,
Is there any question?
sir,
Yes.
sir, in the theory part, we have been taught that there are certain voltage barriers in the diode which we have to cross in order to get it in working condition.
Right. Yes.
So,
So when like the VI characteristics Yuvraj was showing, at that time when we were selecting the diode, we were getting something called VF, right? So that is the voltage that you have to, that is the threshold voltage that you should cross. After that your diode will start working, right? So even like in this particular graph also, you will see there is a dotted line, right? So I think Yuvraj, you can just show it once, right?
This one.
No, so for the VI characteristics of the normal diode, so you have this VF written over there, right?
Yeah. Actually, there's a lag, so I
Yeah,
have
right.
opened the simulation part. So here you can see the plot here, right? Is it coming in your screen?
Yeah, it's visible. It's visible.
So as you can see, until it reaches the 0.3 threshold, the current is passing is 0. So that's what you were asking, right? So yes, it is true.
yes, sir.
What you were saying.
Sir,
So,
but in the output waveform of the half wave rectifier.
Okay.
Right. So for the simulation, Jay, there is like in this particular VLab simulation, it's at the end a simulation tool, right? So here there is no effect of that particular thing. I will probably upload the actual experiment probably within today or tomorrow, because the recording is done. We have to do some manipulation before finalizing the video, but there you can see there are actually many effects other than this kind of results that we are getting from VLab. Here we are like visualizing the diodes as ideal diodes. You don't have those effects in this particular experiment because it's just a simulation to give you an idea that what will happen. I mean, what kind of a waveform you will get. So when you'll see the actual experiment, you will see that there are many things that will come into the picture, right? Like there will be some like DC voltage that will come into the output as well. There are a couple of things that you need to consider while performing this particular experiment. And then if you observe carefully, there you also see a voltage drop that you are asking for. So I think to answer your question, here we are considering the diodes as ideal diodes. You will get all these effects when we see the actual experiments in the videos. Okay, Jay?
Okay, sir.
Yeah. Any other question?
Sir, one thing, sir, am I audible?
Yeah, right.
Yes, sir. Do they have to also find out VDC, VM, IM in every case, like for a rectifier and this one? Means, do they have to write that in the report?
So if they can find it, it will be good. Yeah.
So because below this VLAB section, below the
Right.
graphs, there is
Yes.
one portion where you are finding out the current and
Exactly.
PS
Exactly. Yeah.
calculation.
Yes.
So that also has to be given in the
So they should report it. Yes.
Okay, sir.
Right. Any question by any student?
I have a question. In the slides, there was a distinction between full wave, half wave, and the bridge rectifier. So, the last point, there was some abbreviation TUF. I could not understand what is that.
Jarishmita, can you explain the transformer utilization factor?
Yeah. So this is basically this which point? Which point?
12th point.
Okay. So transformer utilization factor. Okay, so transformer utilization factor, this is basically, see, as you can see, they are of 3 different values for half wave, full wave and bridge. So basically it is the DC out, as far as I think, it is the DC output power to the transformer rating, that is VA rating of the transformer. It is basically the ratio of that. Okay. So what amount of DC output power you obtain at the output?
So
And what
this is the
VA rating
ratio
of
between the DC power output that you are getting from that particular circuit to the effective VA rating of the transformer. So that is your TUF. So actually what is happening in case of your bridge rectifier, if you try to compute that, you are actually getting higher TUF than the full wave rectifier. That's why bridge rectifiers, for 2 reasons. Obviously your TUF is higher, and also you are dealing with a much simpler circuit because you are not using a center tapped kind of a transformer, right? But you are obviously paying more cost because you are using 4 diodes. So TUF is just the ratio of your DC power output of the circuit to the effective VA rating of your transformer. Okay.
Sir, how can we calculate the VI rating of transformer?
How can you
calculate the VI rating of transformer?
So you have to multiply 2 values, the RMS value of your voltage into the RMS value of your source current, and that will be your VA rating of your transformer. I think that should be covered in the class. Is this particular portion covered in the class, by the way? Yes, no, there should be some answer, right? I guess.
Sir, TUF is not covered.
So if it is not covered, I think then it's the multiplication of your RMS value of your voltage that you are getting from your transformer into your current that you are getting, right? So the current that you are RMS value of the load current that you are getting, that is the VA rating that that you should compute with the DC power that you are getting as the output of your circuit. That is your TUF computation for particular circuit. So if it is not done in the class, probably we can circulate a hands-out where the TUF calculation has been done.
Our output and the current are same for full wave and bridge rectifier. So why is TUF different? Hello, sir. Am I audible?
Yes, go ahead. Hello.
Yes, sir. I am saying that the value of DC output power is same for full wave and bridge rectifier. Then why is TUF different?
Yeah.
Hello. Yeah. Am I audible? Yeah. Right. Yes.
Yes, sir. The value of the DC output power is same for full wave and bridge rectifier.
No. The thing is that the average of, I mean, if you try to calculate for the center tap, the effect of that center tap will have something. I mean, because you are doing the center tap, you must know this. I mean, the DC power will be like 2 IM by pi into 2 IM by pi for your center tap circuit, whereas the value for your normal for your half wave rectifier will be IM by pi into VM by pi, something like that. And for your bridge rectifier, what will happen? It will be the DC power will be again 2im by pi into 2vm by pi, right? So that part is correct. But what will happen in case of your VA rating, that will definitely change because you have the center tap in case of the middle circuit. As I said, I mean, probably we can circulate a handout where you can check the TUF calculation for these three circuits, because it will be difficult for us to derive the entire thing right now. We don't have the derivation currently. So the thing that you have to do is that you have to calculate the DC power, but also the VA rating, effective VA rating of the transformer. So that will change for your center tap circuit than the bridge rectifier, because in the center tap full wave rectifier, the effective VA rating will change because of the way you are connecting the circuit. You are not using the entire. So I think Joshmita, can you go back to the actual circuit? So what you are doing is that at a time you are taking half of that particular, yeah. So as you can see that, like, at a time the effective VA rating will change because you are not using the full coil, right? You are taking half of that particular coil and using it for the current flow, right? So the effective VA rating will be changed in case of your center tap, whereas in bridge rectifier you are using the entire coil of the output for the circuit, right? So that's why your effective VA rating for the transformers will change, and that's why the TUF values will be different from your center tap and the bridge rectifier.
Sir, we use half of the coil, but the voltage drop will be the same.
The voltage?
Yes, sir, the voltage will be same because the number of turns will be double.
No. What is number of turns will be double? I could not get that.
I mean, sir, in the transformer for the center tap.
Yes.
So the ratio of turns will be double as compared to the bridge rectifier. So
no,
that
why? I mean, when you perform the bridge rectifier, no. You have the same. So otherwise, it will not work. So this is the same transformer. You have the center tap or you don't have the center tap. When you don't have the, because otherwise, how will you compare? So when you have the same transformer, when you are not using the middle where the center tap, then you have one kind of a circuit. So the number of coils for these two transformers are same. If you change the number of turns in that particular coil, you cannot compare these two circuits. So the effective value for the VA rating for the transformer in case of the center tap will change because you are using the half number of turns in case of the transformer.
Sir, if the number of coils are same in both, then we will get half of the output voltage in the center tap.
Sorry. Can you please repeat your question?
No, sir. I'm saying that if we have same number of coils in both bridge rectifier and center tap rectifier, then in the center tap rectifier we will have half of the one which we discussed.
Right. Yes. So I think if you can look into the sign, what is happening, like the A point and the B point, you have, let us assume that at the center tap position, you have a point C, right? So what is happening, why this circuit is working? Because when you are considering the voltage between the A point and the C point, the center tap point, you have a plus and minus voltage difference between that particular point, right? But if you consider between C and B point, obviously you have the positive point at the C point and the negative point in the B point. When you have a particular waveform, if you reverse it, obviously the points will change, but you are not utilizing the entire coil at that particular time, right? You are using half of the coil at that particular time.
But so what you're saying is, if we consider the center point as C, then
yes,
the number of coils between A and C will be same as the number of coils in the bridge.
No, definitely not. Why?
Only then we will get that V1 by N1.
The amplitude of the output will be half of the input.
Oh. No. What I am saying is probably, I think, I don't have the tablet with me. Devashishta, do you have any graphic tab with you where we can write it down?
No. Isn't there something like Jam for, I don't know, for Microsoft Teams? something like, I mean, that we do in Google Meet, right? There's a jam where we can basically.
No, but we have to write it down, right? Otherwise, I think they are getting.
Yeah, in Google Meet there is a means. I don't know. In Teams, is there anything like that? I don't have anything attached.
Okay, right. Let me. Yeah. So if there is any other question other than the TUF, please ask. I am trying to find a tab which I can attach and then write it down. So the thing that will happen is that obviously the effective rating that you'll get will be like primary VA plus secondary VA by 2 for the entire transformer that you are using for in case of the center tap circuit. But I think you are a bit confused about that particular derivation. So if I can actually derive it, it will be useful for you. So is there any other question other than the TUF rating?
No, sir.
No, right? Fine. So I think the effective VA rating, what should we do then? Yeah, so what I can do is that probably I can, yeah, Yuvraj.
So for the experiments in which we don't have any plots,
Yes.
do we print the oscillator graphs and just attach it in the report?
I didn't get your question. I mean, for the
Yeah, the
experiment.
oscilloscope outputs. I think he's asking if we don't have any graph to be plotted, can we show the oscilloscope output?
Oh,
Yes.
right. Yeah, that should be there in the report. That should be there.
Okay, so we print this whole page and attach it in the report.
Right. Yes.
Okay. Okay.
Right. If there is no other question other than the TUF, probably the best thing to do is to circulate a handout for the derivation, because I think I don't have any option to write down the expression using any graphic tab or anything. So either we have to wait for some time, probably, or we can circulate the hands up. Just give me 5 minutes and then let me check whether I can arrange something for you.
Sir, should I stop presenting?
Let him come back. I think he might be trying something.
Okay.
Yeah. Sorry, I could not get any graphic tab. So, Professor Sen, I think we can share this particular document. I mean, what we have to do is that we have to just show the effective VA rating. That will, I think, work with respect to the primary coil and the secondary coil. So, I think that we can do within an hour or so, right?
Yeah, sure. But yeah, I mean, we have to prepare that document. Yeah.
Yeah, I don't have that particular derivation right now with me, because I thought this particular everything is covered in the class, so I didn't have that particular derivation right now.
Sir, I have a document which shows the derivation.
Yeah, so you can.
Do you have anything like that? So, Ashmita, do you have a document? Do you have a document which shows the derivation? Then we can discuss it right now. If you have it.
Yes, sir. Actually, I have the document, so we can like show them right now. I can upload it, sir, if you want. I can upload it over
So,
here.
yeah, you can upload in the Teams. Then, if it is correct, then probably we can just discuss it, and that should be sufficient. For yeah.
Okay, sir. Okay. Yeah, Yuvraj, can you please stop presenting this once?
Okay.
Is my screen visible?
Not till now.
Yes, ma'am, it is visible now.
Yeah, now it's showing. Yes.
This is the document.
No, but yeah, this is saying the same thing. I think the derivation they are looking for, and they are confused about how to calculate the VA rating.
So this is for the center tap full wave. This calculation is there. And so this is for the bridge rectifier. This particular calculation is there.
I think you're moving too fast. We are able to follow.
Yes. Yes, sir. This is for the center tap situation.
Yes, go ahead. Somik, are you able to see? Somik? Yeah. So that's.
Yeah, that is the expression. The expressions are correct, but I think I don't know whether they can understand what is the VA rating from this particular example or not, because the derivation is actually correct what they have done, but probably the explanation I don't know. I have not seen this document before. So
we need to verify this. I am unable to follow. I don't know whether you followed or not, but some electric baba. Okay, we have to verify this. What is this?
yeah, I mean we cannot actually. Yeah, so I think it's better if we can actually like circulate the document rather than referring to some.
Yes. We will do it and we will share. That's better.
I think that would be better. I mean, the question is already raised. I think we can answer this because the derivation requires the explanation of the effective VA rating part. So I think it will be better if we can actually, circulate that particular derivation part rather than referring to some other document.
Yes, sir.
Thanks, Joshmita. But I think what we'll do is that we'll try to circulate that particular document within an hour or so.
Sure, sir.
Yeah. Like any other question by any student? So if not, Professor Sen, is there anything to announce? Probably the next week's class, right?
Yes, next week, yeah.
So there will be no class in next week. We'll meet next to next week in the same time for rest of this particular experiment because we have not discussed the Zener diode circuit as well. So we have to discuss in the next to next week. There will be no class in next week, and we'll try to answer the question that has been raised in the class about the derivation of TUF. Within an hour or so, I have to just go back to my room because the graphic tab is not there. Sorry for that. So we'll answer that within an hour. Thank you.
Yeah. So you all have some kind of tests, right? We believe that because the institute has allotted that 1 week for tests, so that's why we are giving that break. Okay, on the test week. You have your tests, right? You might be having some tests in some of your courses, right?
Yes, sir.
Yeah. So that's why we are giving the break next week. Okay, we meet the next to next week after 2 weeks for the remaining of the class, the remaining of the experiment.
Sir, so the deadline of the previous assignment will remain the same, or will it get postponed?
That deadline remains the same. Deadline does not change.
That will remain same. Yeah.
Deadline is remaining the same. Okay. And we will announce. I mean, the deadline for this one, it will be basically 3 weeks from today because 1 week there is a break. Usually it is supposed to be 2 weeks, but we are extending by 1 week because we don't have a class. It will be 3 weeks from today. Okay, any other question? Okay, Professor Bhattacharya, I think we can conclude.
Yeah, I think we can conclude and we'll answer that particular question by uploading a document within an hour or so. Yeah, thanks for joining.
Thank you, sir.
Yeah,
Thank you, sir.
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 Yeah, thanks.